In this video, we're going to take a look at three important vectors, which we'll refer to together as TNB, that help us understand the geometry of a given curve. The three vectors we're going to consider, T, N, and B, have important geometric properties. If we look at a curve and choose some point along that curve, the unit vector T is going to point in the direction that the curve is moving. The principal unit normal vector N is going to point in the direction the curve is turning. The unit binormal vector B is going to point in the direction perpendicular to both T and N. We can see in this animation that as we move the point around the curve, the vectors move along with it, continually pointing in their prescribed directions. We can see that when we take these three vectors together, we get a right-handed system, which is called a Frenet frame or a TNB frame, which allows us to establish a coordinate system with any given point as its origin. These then together help us define the local geometry of a given curve. Our unit tangent vector is already a familiar concept. We've seen before that we can take the tangent vector, r prime of t, and divide it by its magnitude to get a unit tangent vector. We can also think of this in terms of arc length of a curve. If instead of r of t, we define our curve as r of s, where s is the parameter for arc length, then we know that r prime of s, the magnitude of that, must be 1. So if we happen to have a curve that's been parameterized in terms of its arc length, its unit tangent vector is then just the same thing as its derivative vector. The unit normal vector points in the direction that the curve is turning. In other words, it tells us something about how the unit tangent vector is changing. Therefore, the definition of the unit normal vector is it's going to be the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. The unit binormal vector is perpendicular to both t and n, pointing away from the plane formed by them. We know that to create an orthogonal vector to two vectors, we can take their cross product. And the unit binormal vector is in fact defined as the cross product of the vector t with the vector n. Some key properties to keep in mind as you work with these three vectors is that t, n, and b are mutually orthogonal. In other words, any two of them, when you take their dot product, you'll get 0. Each of them has unit length, so their magnitudes are all 1. And together they form a right-handed coordinate system. Let's work with an example. Here we have the curve r of t equals cosine t sine t t, and we want to find all three vectors for this. So we'll start with t. We know that t is going to be r prime of t over the magnitude of r prime of t. Well, that is going to be the vector negative sine t cosine of t 1 divided by the square root of sine squared of t plus cosine squared of t plus 1. So here we have the vector 1 over the square root of 2 times negative sine t cosine t 1. N is then t prime of t divided by the magnitude of t prime of t. That is going to give us, taking the derivative, we get 1 over the square root of 2 times the vector negative cosine of t, negative sine of t, 0. divided by the magnitude of that, which is 1 over the square root of 2 times the square root of cosine squared of t plus sine squared of t, which is 1. So we end up with the vector negative cosine of t, negative sine of t, 0. The last vector we need is the vector b, which we know is going to be t cross n. So if we take the cross product of these, may move k over a little bit. We're taking our determinant, so we're going to get 0 minus negative sine t, which is positive sine t, times I, minus, and then we get 0 minus negative cosine t, so that's 0 minus negative, so we get negative cosine t times j. And then last but not least, whoops, I wrote a 0 there instead of a k. That's a little strange. We get sine squared t minus negative cosine squared t, which is 1 times k. So our vector b is the vector sine t, negative cosine t, 1. All right, in this example, we have the vector valued function t ln of cosine of t. We're going to find all three vectors and show that they are mutually orthogonal. Now we can see that our function lives in the xy plane, right? There's no z coordinate, which tells us that our vector b, the one that is orthogonal to both t and n have to live in the same plane as the curve. So the vector b is probably only going to have components in the k direction, but we'll see what happens. See if my prediction comes true. So let's look at the vector t first off. T is going to be r prime of t divided by its magnitude. And so if we take the derivative, we get 1, and then the derivative of the natural log of cosine of t is 1 over the cosine of t times the derivative of cosine, which is negative sine t. I'm just going to leave the magnitude of r prime down here for now. So we see that this is 1 negative tangent of t over the magnitude of that. This should be a vector symbol, not an absolute value. And so that is going to be the square root of 1 plus the tangent squared of t, which is of course the secant of t. So we have 1 negative tangent of t divided by the secant of t, because 1 plus tangent squared is secant squared, and then we take the square root. Well, secant is 1 over cosine, so this ends up being cosine of t. And then when we divide negative tangent, which is sine over cosine, by 1 over cosine, we get negative sine of t. All right, our vector n. This tells us how fast our unit vector is changing, so it's going to be t prime of t over the magnitude of t prime of t. So that is going to be the vector negative sine t, negative cosine t, all over the square root of sine squared plus cosine squared, which is of course 1, and so we get negative sine t, negative cosine of t. And then we'll find our vector b. B is the cross product of these two, t cross n. So we're going to add our k column here because we need that third dimension in order for the vector b to exist. So we're going to write this as cosine t, negative sine t 0, and negative sine t, negative cosine t 0. And so we're going to get, let's see, when we do our determinant for I, we get 0. When we do our determinant for j, also 0. When we do our determinant for k, we're going to get negative cosine squared of t minus a positive sine squared of t, so minus sine squared of t, which is negative 1. So we get the vector 0, 0, negative 1 for our vector b. Now, we were also charged with showing that they're all unit vectors and that they're mutually orthogonal. So let's go back and do our magnitudes. The magnitude of t is going to be the square root of cosine squared t plus sine squared of t, which we know is 1, so that one checks. The magnitude of n is very similarly the square root of the sine squared of t plus the cosine squared of t, which is 1. And then the magnitude of b is just the square root of 1, which is 1. So that checked out. Now we're going to do our mutual orthogonality. So first I'm going to do t, not t cross, but t dot n. I'm doing dot products. The dot product of t and n is going to be the sum of negative cosine of t sine t plus sine t cosine t, because those two negatives cancel, which is in fact 0. T dot b is going to be 0 plus 0 plus 0. And similarly, n dot b is 0 plus 0 plus 0. And so we see that they are, in fact, all mutually orthogonal. So what we see is when we construct these vectors, this Frenet frame or TNB frame becomes a moving coordinate system. It's built from tangent normal and binormal vectors, which are all unit vectors. They have magnitude 1, and they are all orthogonal to one another. This helps us to understand the geometry and orientation of our curves, independent of any motion along them.